Hey guys, in this video we're going to start talking about section 1.9, further limit calculations using algebra. And so our main focus today is to look at different equations and how we can employ different strategies to find their limits when they're not continuous functions. So before we get into this, let's just kind of talk about what we looked at last week. So we had two different strategies that we used for equations. So the first strategy was when we had continuous functions. Continuous functions were easy to take the limit of because all we have to do is plug in whatever x is approaching into our function. So like for example, we had something like find the limit as x approaches 5 of 3x squared plus 2x. And since this guy is continuous, all we had to do is plug in 5 into our function for x and evaluate. And so we get 75 and 10 makes 85. And so the limit as x approaches 5 of 3x squared plus 2x is 85. So that was probably the easiest case that we have, continuous functions. We also did something where we looked at limits at infinity. So maybe we had something like this. And the way that we dealt with these, so this was limits at infinity. How did we deal with these? Well, remember the trick was to divide top and bottom by the highest power term. In this case, the highest power term is x to the third. And so what we did was we divided everybody by x to the third. And then we simplified this out a little bit. So let's go ahead and do this. We got 1 plus 1 over x to the third over 2 over x minus 9 over x. And then we plugged in infinity to see what would happen as x gets close to infinity. So we already employed these two strategies. Now, the next thing we're going to do is we're going to talk about how to use factoring and multiplying by the conjugate to simplify these limits. All right. So the first thing I want to do is I want to look at this example. This is a rational function, x plus 1 over x minus 3. And the reason it's rational is because we have a variable in the denominator. X is in the denominator. And so if you were to plug this into Desmos, this equation right here, x plus 1 over x minus 3, you would get a graph that looks like this. And, algebraically, we can see that x cannot equal 3. And so we have this vertical asymptote at x equals 3, right? So this blue dotted line is where the function does not cross. And there's really nothing we can do here. There's no tricks we can use because we don't have a limit at infinity. And so really the only thing we can do is to look at this graph and see what the limit is. And it turns out that the limit does not exist because this x minus 3 can't go anywhere. And so we end up getting, if we plug in 3, for x, we end up getting 4 over 0, which is undefined. And so the limit does not exist. Now, how can we see this from the graph? Well, if we're coming from the left, as we approach x equals 3, we can see that this thing goes to negative infinity, because it goes down forever. But if we come to the right, if we're approaching x equals 3 from the right, we're actually going to positive infinity. And so in both cases, the limit does not exist here. What about something like this? Evaluate the limit as x goes to 3 of x squared minus x minus 6. Well, again, we have this issue where if we plug 3 in, the denominator is 0, and we don't want that. But this is actually a special kind of function because if you were to graph this in Desmos, you'd get a line. And you wouldn't see this hole right here, but if you were to click in that spot, it would say undefined. And that's because there is what's known as a removable discontinuity there. Why is it removable? Well, here's what I'm going to do. The top I can factor, right? Remember how to factor these quadratics? We look at the last term, we say to ourselves, what two numbers multiply to -6 but add to -1? And that's going to be x minus 3 and x plus 2. So we can factor the top, and the bottom is just x minus 3. And now we can see that we call it removable because these factors can cancel. And so we're just left with x plus 2. So this function is the same function as x plus 2, but the one that doesn't cancel the x minus 3 has a hole right there. Okay? And so that's called a removable discontinuity. Because when we factored, we literally removed it right here. We were, we divided it out. And so from here, well, there's no problem with plugging in 3 in for x. And so we can just do that. We can plug in 3. And so the limit, as x goes to 3, is just going to be 3 plus 2, which is 5. So that's our answer. So the first thing we did was we factored. Always check to see if you can factor first. Then we removed the removable discontinuity. And finally, we plugged in whatever x is approaching in for x to see what our limit is. And we can see from the picture, from the graph, that indeed the limit is going to be 5 as x goes to 3 from the left and the right side. And remember with limits, it doesn't have to be defined there. It just has to approach that value. So our answer here is going to be 5. Let's look at this one. So again, if you were to put this in Desmos, you would get a line that looks like this going through the origin. And this little hole isn't going to be there, but if you try to click on it in Desmos, it's going to tell you undefined. And that's because our graph, 3x to the third over x squared, which is what is pictured right here, is undefined when x is 0, right? Because if we plug in 0 in here, we get 3 times 0 over 0 squared. 3. And we end up getting 0 over 0, which is not good. But what we can do is we have a removable discontinuity. And we get that because 3x to the third over x squared can be simplified, right? This guy, x squared, can go away, and then one of these x's can go away to give us the line 3x. And so 3x to the third divided by x squared looks the same as the line 3x. The only difference is in the latter, or the former, the 3x to the third over x squared, we have a hole at 0, whereas 3x, there is no hole, right? And so all we have to do at this point is plug in 0 for x, and we get that the limit is equal to 0. So our answer is 0, and we can also see this on the picture. If we're approaching x equals 0 from the left and the right side, we can see that y is converging on 0. Okay. All right, let's do this one. Okay, so now our variable is t. That's okay. We always want to see if we can factor top and bottom first. So the top, I can pull out a GCF. The biggest thing I can pull out is t squared. And on bottom, the biggest thing I can pull out is t squared as well. Now, when I divide each of these guys on top by t squared, what I get on the inside is t squared plus 1. And on the bottom, I get 2t minus 9. All right. And now we have a removable discontinuity. These t squareds can cancel. And now we're left with t squared plus 1 over 2t minus 9. Of course, we're still taking the limit. I'm just being a little bit sloppy here, not writing this. But now we don't have a problem if we were trying to plug 0 in for t, because in the original problem, if we plugged in 0 in the denominator for t, we would end up getting 0 in the denominator. But here we don't. Okay, so here we don't. Oops. If we plug in 0 for t, we get 0 squared plus 1 over 2 times 0 minus 9. And that's going to simplify to negative 1 over 9. So that is our limit. That's our answer. All right, let's look at this one. So we always want to see if we can factor. Now the top we can factor because it's a difference of squares, if you remember that from Algebra 2 or college algebra or whatever. The top, the difference, this is the difference of squares. Which tells us that a squared minus b squared is equal to a plus b times a minus b. Okay, so that's the difference of squares, and so we can factor the top as x plus 3 times x minus 3. And on the bottom we can factor this thing too, because what two numbers multiply to give us negative 12 and add to give us positive 1? Let's see. How about positive 4 and negative 3? So x plus 4, x minus 3, I think that'll work. Yep. And then we have a removable discontinuity, which is this x minus 3. And so we just get x plus 3 over x plus 4. And here we don't have a problem now if we plug in 3 for x. Originally we did. We got 0 in the denominator. But here we do not. If we plug in 3 for x, we get 3 plus 3 over 3 plus 4, which is 6/7. So that is our limit. Okay, let's do this guy. All right, so notice we have a problem. We can't plug in 0 for h because the denominator gives us 0. So we need to kind of mess around with this. Well, the first thing I notice that I can do is, I can go about this a couple different ways, but the thing that stands out to me is that I have 3 plus h squared, and so maybe I can FOIL that. Let's go ahead and do that. And keep everything else as it is. So when I FOIL 3 plus h times 3 plus h, I get 9 plus 3h plus 3h is my inner, and then plus h squared is my last. So I have that so far. And, I am being sloppy here because I keep missing the limit, but maybe we should just carry it over here to not be sloppy. Let's do that. Okay. All right, so now on top, these 9s can cancel, and I end up getting 6h plus h squared over h, limit as h goes to 0. And what I can do at this point is I can factor the top by taking a GCF of h out. And so maybe I can scroll down a little bit here. So I take h out, 6 plus h over h, and now I have this removable discontinuity. These guys cancel out, and now I'm free to plug in 0 for h because there's no more denominator, no more problems. No more denominator, no more problems. So 6 is my answer. That's my limit. All right, let's do this. This looks a little interesting. So I look at the top. I don't see any factoring that we can do. I do see that if we were to try to plug in 4 from the get-go, we would have a problem. So we need to ensure that the denominator is not 0. What can I do? Well, the first thing I can do is I can actually subtract these on top. So let's do that. And just looking for what are the things that I can do. Okay, so let's see what I can do. Okay, so I want to subtract these guys. I want a common denominator. So if I multiply these, my common denominator is 4x. And so maybe I'll write it vertically like this. So my common denominator is 4x. So over here, I have to multiply by x on top and bottom. So I get x over 4x, and up here I have to multiply by 4 on top and bottom. Should probably, let me write this again. How about we do times x like that, times x times 4 times 4. Okay, and then we can combine the numerator since we have the same denominator. Okay, so this became 4 minus x over 4x. So that's the top. We just got common denominators and made it into one fraction. And the bottom is still x minus 4. Okay. All right, so I'm going to erase this. I'm going to erase this right here. So the next thing I can do is I have complex fractions. And when I do that, I can keep the top fraction, which is this, multiply by the reciprocal of the bottom fraction. The reciprocal of x minus 4 over 1 is 1 over x minus 4. Okay, and then I can multiply straight across, but I'm gonna leave, like, because what I'm noticing is that these guys in purple are almost the same, but not quite. So I'm just gonna kind of leave them in that form for now when I multiply across, and not, you know, fully multiply 4x by x minus 4. Because, you know, even if we, at this point, if we're taking the limit as x goes to 4, we're still going to have a problem. You always want to ask yourself, do I have a problem? Yes, I have a problem, because if I plug in 4 in here, I'm still going to get 0 in the denominator. So I can't do that. But what I can do is I can make the, oh, I actually meant to put x minus 4 right here. I can make the top and the bottom cancel out, but I have to do something first. Notice that the top can be written, if I factor out a negative in the top, I get negative 4 plus x. And think about that. Why is that true? Well, if I FOIL back the negative, I end up getting what I started with. So yeah, we factored it right. And guys, minus 4 plus x is the same thing as x minus 4. And so I have a removable discontinuity here. And I'm left with negative 1 over 4x. Of course, forgot the limit. Limit as x goes to 4. And now we don't have a problem in the denominator. We can just plug in 4 for x and evaluate. Okay, so let's do that. So we have negative 1 over 4 times 4 is equal to negative 1 over 16. And that's my answer. Okay. All right, so whenever you're doing your homework and you see square roots, you should think to yourself, first, let me try to do something with the conjugate. So what is the conjugate? Well, the conjugate is basically taking, it's probably easier to just show you. So like, if I have either the numerator or the denominator of the square root, the conjugate is the same thing, except I change the sign of what's not under the radical. So instead of root x minus 1, it's root x plus 1. We just change the sign. And so the first thing you should try is multiplying top and bottom by the conjugate. That's a little trick. And what that is going to do, it's going to get rid of a square root. Okay, so sometimes it can help, sometimes not, but let's just check it out to see if it does anything. Okay, so multiplying by the conjugate, Same thing as multiplying by 1, so we're not doing any kind of magic tricks here. But we do want to FOIL, okay? So on top, if I do root x times root x, I just get x, right? And then I have outer, which is plus root x, inner, which is minus root x, and last, minus 1 times positive 1 is a minus 1. These guys cancel. Okay, and on the bottom, you know, I'm not going to do anything quite yet because I'm going to see if I can cancel out any factors. And it turns out I can because, let's see. On top, I get x minus 1. On bottom, I have x minus 1 times root x plus 1. And these guys cancel out. So I'm just left with limit as x goes to 1 of 1 over radical x plus 1. And now I'm in a good position because if I plug in 1 for x, no problems with the denominator. It's not equal to 0. So let's plug in 1 for x. And I end up getting 1 over 2. So that is my answer here. So yeah, whenever you see radicals, you should think, let's try to multiply by the conjugate. All right, let's do another example with radicals. So this time, you know, again, we leave whatever is under the radical as it is. The only thing we're changing is the sign of this constant number, okay, when we multiply. And so when we multiply by the conjugate, we're going to multiply by 9 plus h times positive 3. Okay, that's the conjugate. And so whatever I do to the top, I better do to the bottom. So I also have to multiply the bottom by root 9 plus h plus 3. And then I can do my foiling. So up top, when I FOIL, okay, so root 9 plus h times root 9 plus h is just 9 plus h. Outer is going to be a positive 3 root 9 plus h. Inner is going to be a negative 3 root 9 plus h. And last but not least is going to be a negative 9. So that's all on top. And on bottom, I'm just going to kind of leave this multiplied but not get crazy because I want to see if things can cancel out. Okay, so on top, I have this guy and this guy cancel, and this guy and this guy cancel, and actually, I'm in a good position because I have h over h times this business. Okay. And I'm taking the limit as h goes to 0. And what's nice is once I cancel out these h's, I no longer have a problem in the denominator. I can just plug in 0 for h and evaluate. Okay, so let's do that. Okay, so if I plug in 0 for h, I get 1 over root 9 plus 0 plus 3. Okay, so root 9 is 3. So I end up getting 1 over 6. That's my answer. Okay, guys, I think I'm going to go ahead and stop this video here. We're going to pick back up in the next video with the squeeze theorem. So thanks for watching, and I'll see you guys in just a bit. Hey guys, in the last video we left off right here, and so I wanted to finish this section off by talking about the squeeze theorem. This is still 1.9, it's at the very end. And so this is a pretty famous theorem in math. Sometimes it's called the sandwich theorem, but anyway, either one, squeeze theorem or sandwich theorem. And I kind of just want to demonstrate how it's used first and then sort of explain the theorem. So basically what we have here is a situation. Okay, we have f of x is some function that's bigger than or equal to 6 minus x squared, less than or equal to 6 plus x squared. And so the limit is going to be, we want to find the limit of the functions on either side, and if it turns out they're the same, then that's the limit of the middle one. All right, so first thing, what is the limit as x goes to 0 of 6 minus x squared? Well, this is a continuous function, right? It's a polynomial. So we just plug in 0 for x, and we get that the limit is just 6 minus 0 squared, which is just 6. Okay, so the limit of this is 6. What about the other side? So we have the limit as x goes to 0 of 6 plus x squared. And again, it's continuous, so we can just plug in 0 for x, and we get the same thing. We get that the limit is 6. So since on either side of f of x, the limit is 6, the limit of f of x is also going to be 6. That's what the squeeze theorem says. So, yeah. And we can do the same thing for this function right here. And I encourage you to pause the video and see if you can get this one. Okay, so we want to know what is the limit of f of x as x goes to 2. So let's first take the limit as x goes to 2 of this leftmost function, 5x plus 2. And this is continuous, so we can just plug in 2 for x to get 5 times 2 plus 2, which is 12. Okay, so limit of this is going to be 12 as x goes to 2. And as x goes to 2 for this guy, let's see, limit as x goes to 2 of x squared plus 8. Well, again, this is continuous, so we can just plug in 2 in for x and evaluate. We get 2 squared plus 8. And that's also going to give us 12. And so since the limits of the function on either side, that, basically the way you can think about this is the thing that's being sandwiched in, okay? Since the limits are the same on both sides, and the limit as x goes to 2 of f of x is also 12. Okay, so that's kind of how the sandwich theorem works. Let's take a closer look at this. All right, and so we use the sandwich theorem when all of the other techniques can't be used. So we learned a bunch of different ways to do this. We used factoring to remove discontinuities. We divided top and bottom by the highest power term for limits at infinity. We used graphs. We did all kinds of stuff. This is just another way that, just another tool in your toolbox for limits. Okay, so here we have a function x squared times cosine of 1 over x. And I have the graph of this function right here. And we are interested in what is the limit as x goes to 0, okay? And if we look at the graph, it looks like as x goes to 0, y also goes to 0, right? It looks like it's getting pretty close to the y-axis, but let's prove this algebraically with the squeeze theorem. Okay, and I'm going to show you how to do it. So, okay, here is what the squeeze theorem actually says. Okay, and we're going to go into detail with this. The squeeze theorem says that if we have a function squeezed between two other functions, then the limit of, and if the limit of the two functions is the same as x approaches some value, then that's the limit of the middle function, just like we saw for this example and the top example, okay? So our function that we have in purple was x squared cosine of 1 over x. So in purple, we have x squared cosine 1 over x. And we want to see what the limit is as x goes to 0. So, question. What is the limit as x gets close to 0 of this function, which we see in the graph as purple? Well, we can use the squeeze theorem. We need to pick a function that is always going to be above x squared cosine 1x and a function that's always going to be below it, near x equals 0. And the way that we can do this is in the following way. We know from trig that cosine of an angle is going to be between 1 and negative 1, right? We know that from trig. That's a true statement. Cosine of an angle, the angle happens to be 1 over x, is always going to be between negative 1 and 1. And so to make this thing look like this guy, we can multiply the middle by x squared, and then everybody else has to be multiplied by x squared as well. Remember, 1 times x squared, and then on the other side, we have minus x squared. Okay, so now we have a really good, we have good functions for the squeeze theorem. So this guy is our a of x. Okay, so this is x squared in our case. And this guy is f of x, the thing in the middle. And then on the other side, that's our b of x. So that is going to be this guy. This is negative x squared. Okay? And I have these functions graphed. So in red is negative x squared. As you can see, it's this like upside down parabola. And then in green, I have positive x squared. And you can see that the function that we're interested in, this purple function, x squared cosine 1 over x, is sandwiched between negative x squared and positive x squared close to 0. Maybe we can, maybe like draw a box around it like this. So when x is close to 0, this purple function is sandwiched between the green and the red function, as we have here with this inequality. So, all right, what does this tell us? Well, what's the limit as x goes to 0 of negative x squared? Well, that's going to just be 0, right? It's continuous. We just plug in 0. So this guy is 0. And same thing for this guy. The limit is also 0 as limit as x goes to 0 of positive x squared is also going to be 0. So the sandwich theorem, the squeeze theorem, tells us that this limit, that the limit as x goes to 0 of that middle function is also 0 because the two functions on the outside are going to 0. Okay, so that's our answer. The limit is 0, so we verified this using the squeeze theorem. Okay. Let's do this one right here. So now we're interested in what happens when the limit goes to, the limit as x goes to infinity of sine of x over x. Well, again, we want to do a little trick to use the squeeze theorem. We want to sandwich this guy in between a bigger and a smaller function, okay? So how can I do it? Well, let's think about this, okay? Sine of x, so sine of x, again, we can do this trick. We can say the sine of x is between negative 1 and 1. That's what we learned from trig last, or whenever you took trig, if you took trig. And so to make it look like the function that we have to divide everybody by x. Okay, so when I divide everybody by x, I get this. Okay, and so now, let's see, what did I do? I did the left red and the right green. So this is my leftmost function, this is my rightmost function, and this middle is my purple function. And so I know what happens when the limit as x goes to infinity of negative 1 over x. Well, as x gets really, really big, this thing is going to go to 0. Okay, that's 0. In a similar way, if we take the limit as x goes to infinity of 1 over x, As x gets huge, this thing also converges to 0. Okay? Therefore, since the functions on either side of the function we're interested in, since their limits go to 0, the one in the middle goes to 0. So we can say it fancy. We can say, therefore, by the squeeze theorem, the limit as x goes to infinity of sine x over x is going to equal 0. Okay, that's our answer here. Okay, let's do one more example. We want to take the limit of e to the x times sine of x as x goes to negative infinity. All right, well, let's do our trick again with sine of x because we know how to bound this thing. We know that sine of x is between -1 and 1. And to make it look like our actual function that we're interested in, we can multiply everybody by e to the x. So this becomes e to the x sine of x is less than or equal to e to the x greater than or equal to minus e to the x. Okay? All right, so as x goes to negative infinity in both of these functions, e to the negative e to the x and e to the x, this thing is going to go to 0. Right? And let's look at this on a graph. Okay, so let's see. Let's do negative e to the x. All right, notice as x gets smaller and smaller and smaller, negative e to the x is going to 0. Okay, we can see that. And then with positive e to the x, we get a similar phenomena. So we get, if we do e to the positive x, well, again, in this green graph, as x gets smaller and smaller, this thing is going to go to 0. Okay, so the limit of both of these, so the limit, let's write it right here, the limit as x goes to negative infinity of negative e to the x is equal to 0, and the limit as x goes to negative infinity of positive e to the x is 0. So since this is true, then the limit as x goes to negative infinity of what we were interested in to begin with is also equal to 0. Okay. All right, guys. Well, that was my spiel on the squeeze theorem. I'll see you guys next time. We're going to talk about derivatives and how we can use these limits to actually, answer questions about physics and stuff. So thanks for watching. I'll see you guys next time.